So, hello everybody, and as you can see in this slide, everything that I will talk about today is about the continuous learning, continuous improvement, and how we can use GenAI in accelerating those activities. Most of the outputs that I will show you in this project, in this presentation, is basically the outcome of this project that is a collaboration between Volvo Cars, Chalmers, and Zenseact, and is funded by Vinnova and VASP. So what's the goal there? During our development and basically doing the design of all the functions, we have a lot of brainstorming techniques. We come up with, for instance, the hazardous events, and then when we implemented the function, is there any problem? No.
Yeah, there's a cracking noise.
Oh, okay. Okay. So as you can see in this case, there are scenarios that you don't foresee, and then we want to collect the data regarding those scenarios. So later, we can learn from them and improve the function. And there are a lot of scenarios that we might think about them, but maybe not in this specific orientation, basically. And we collect all of those data, and then we learn from them, and at the end, we update the software in the car of the customer, and then our customers, they have every day better and better experience with respect to our functionalities. So, in simple words, what are the goals? We collect all of the scenarios, unknown limitations, and then we update the software to improve the functionality. And then when we have enough confidence on our function, we basically update the software in order to expand the operational design domain or expand the functionality in the customer vehicles. And we want to do it in the fastest way. And GenAI is one of the approach that we can basically employ to get this, making it rapid. There are concepts such as DevOps that you every day experience in your cell phones, laptops. Every day you get a new update, and then you update your software, but it doesn't go always well. Sometimes you get these kind of messages, and this is a real case in one of the updates in one of the operating systems. So here we are handling the safety related scenarios, and we want it to be safe. And if you integrate the safety activities to these loops, it will lead to something similar to this. It's a bit asymmetric, as you can see, because we have a lot of development activities there. We have specification, design, and so on and so forth. And there are a lot of challenges to basically to prohibit us to have that much of the speed there. And if you're interested to know more about the details of that, you can always go to our papers, or I normally also put the papers there so you can read more. So if we zoom in a bit to each of those activities, everything starts from the specification and design, and then when we have the hardware-ready vehicles, meanwhile, you can also update the software or work on the software, and when the software is ready, you test the software, you test the integration of the software. If everything is done, basically you update the software. But we don't stop there. We continue with the field monitoring, and when we have enough confidence on the function, we perform ODD expansion. This figure is very important because during the slides, I will come back to each of those elements and show you a snapshot of how GenAI can be used in each of them. So, and this is an iterative, basically, way of working. How do we want to do that? One approach is to use GenAI. There are a lot of these models, large language models, vision language models, and recently vision language actions as well that you can use in your driving scenarios. And you can generate code out of them, you can generate pixels, you can generate videos as well. This is basically some videos that I asked from Sora to generate some kind of scenarios that there are moose in them. Although they are a bit funny, but yeah, we don't use them in our testing. But the issue with LLMs is that they are not at all deterministic, but they are not also that much stochastic. So sometimes their output makes sense. And most of our works at the start started with that we wanted to basically publish something that for safety related things, don't use these models, they are stochastic parrots. But at the end, when we studied in basic more rigorous way, we understood that they have some advantages and some disadvantages. But one thing that you need to know about these kind of new technologies is that regarding the evaluation of them, sometimes you need to be careful. For instance, in testing of the LLMs, one of the threats to validity of most of the works that they are done or research that are done is basically the benchmark leakage. Most of these benchmarks that they exist for the existing papers, they are known benchmarks that these LLMs, they might train on. So you can't that much normally trust to those. That's why we designed also an imaginary function to see that if these LLMs are actually capable of doing novel tasks, or they are like a library that you can just ask something and then they get something out of their learnings, basically. And to make them more productive or efficient and also reliable, you need, there is one way that you can have basically use them as a chatbot and the user basically communicate with them, like what you do with systems like ChatGPT, or you do it in some kind of more orchestrated way, that the task that is get from the user, it will be go to the orchestrator, and then orchestrator decide which model it call. Is it, for instance, needed to do some kind of retrieval augmented generation or RAG? Or, for instance, is there any need to do some search in the internet for them? And also connect the response to some kind of environment that we have there, like simulation environments, hardware in the loop, or vehicle in the loop. Or we need some other models, like vision language models. So now, with knowing that, if we start from the first step, specification and design, basically in that task, I got one sample task. It's a hazard analysis risk assessment. So basically, I don't want to train you on the hazard analysis risk assessment. It's a tough task. Basically, it's a brainstorming task that you think about what can go wrong in your function. And then you understand that if it's safety related or not, and if it's safety related, you come up with some requirements in natural language mostly. So you need to, then in this case, we started to break the task to so many subtasks, and each of those LLMs, they are expert in one of those tasks. And we created a multi-agent system. This is a work from 2 or 3 years ago, and those days multi-agent system was not actually a thing. It was mostly a chatbot thing. And there, all of these basically agents, they talk to each other like a team of experts, and then they come up with the final results. And all the results, for sure, they are also recorded, and that's the basically actually outcome of the pipeline. And then it has multiple steps. I don't go to the details of the steps. And at the end, it come up with the severity identification. It will come up with the requirements, and also it has some kind of reviewer. But if you want to use also your daily, your basically data that you collected during your operation phase, you can also use vision language models to translate all of these frames into scenarios, and then you can run this pipeline over your recorded data as well. And then you can name it, for instance, runtime hazard analysis risk assessment. And then in that experiment, we sent it to some experts to review without biasing them that if it's a LLM or a human expert. And overall, the results was satisfactory. And if you did this task in your company, you know that your reviewers, they never are satisfied with your results. So what we judge is that it is acting somehow as a junior engineer. Maybe it's not a senior, but junior engineer. And it's a good start, basically. But that was, all the communication was in natural language. Here is another example, but in the similar basically domain. If you, this is basically an example by one of the safety experts to criticize that LLMs, they are not suitable for engineering tasks. If you ask them to generate a glass of water which is filled 90%, you get something similar to this. And if you measure, you see that it's not 90%, it's 70%. And if you work in the safety-related domain, you know that reliability and this kind of stuff is very important for us. So maybe we shouldn't use them. But if you change basically the way of working with them and you ask for a code, I basically ask for the same prompt, but in this one, it generates a code for you. And if you run that code, you will see that, okay, it generated basically a glass of water and it's very accurate, but maybe not as nice as the previous one. So maybe we can use these models also for code generation, and maybe it's even better than the natural language as the output because it doesn't have that much of the ambiguity as well. So then we go to the software step. And there we have basically two main paradigms. One is the rule-based and the other one is machine learning-based. In rule-based, you come up with the logic, your designers, and then you implement them. In machine learning-based, you have data and the model learn from the basically data. You know that, I guess, well. So if we zoom into the conventional software and rule-based software, what we did is that we connected this basically LLMs to a simulation environment. And then we use the simulation environment as some kind of filter to a concept that we name it generate fast, eliminate fast. So the pipeline is like this. You give the function description to the LLM, and then the LLM generate the code for you. And then the code, if it's compilable, sometimes it's not compilable, and we try to make it fully automated. We didn't want to have human in the loop because I know that if we put human also in the loop, more or less you get what you want after some iterations. So we wanted to see that if we can automate it and brute force it. So basically, it generates the code, and that code will be tested against multiple scenarios. In this case, as you remember, I mentioned benchmark leakage. We defined a new function. Basically, it's an unsupervised collision avoidance by evasive maneuver. So this car doesn't have any braking system, and it only avoids the collision by changing the basically lanes. Don't worry, it's not in the car. It's just for the purpose of the experiment. So basically, at the end, this pipeline generates the codes with the test report, and you can use that as a evaluation technique for how good is this code. And then it will be sent to the reviewer. And the nice thing is that you can have you can have confirmation bias basically there. And then the nice thing is that you can use those failure cases to also check your reviewers to see that if they are awake or they just push the button and say the code is okay. And then you send it to the other environments as well. And here are the results. I don't go to the detail, but simply the green means that it was successful. And we did this experiment with multiple open source models and also cloud-based models. And as you can see, we tested for 4 functions, F1 to F4. F4 is the function that I described, which is the most reliable one for this experiment. And the others, they are simpler. The more difficult the task become, the less success rate we have. And the less benchmark leakage we have, again, the task is more difficult, but still some of those models, they can be successful. Especially it's very interesting with the open source models. For instance, Mistral could be successful for adaptive cruise control generation. So in short, basically it will lead to something similar to this, that it generates so many codes, they will run, and then at the end, you will pick the successful one. Well, that's good, but there is an issue there. There is no conversation between LLM and another thing. But what if we create a conversation between LLM and a simulation environment? So basically, the LLM generate the code, and then the simulation environment respond back. And then we can close the loop, and this LLM can continuously generate modify the code and fix maybe the bugs. And here is one example. This is a real example, actually. So we gave the LLM the function description, it generates the code, and then the code is tested. On top, you see basically the test report there. And then later it will be sent back to the LLM as a feedback. Sometimes it's successful, sometimes it's not. And as you can see, some of these test cases, they are a bit difficult. It's like a hijacking scenario. So like this case, for instance. There are two cars that they are trying to block you. And as you can see, it's interesting that the LLM is quite creative. It also changed the lane in a non-conventional lanes. And then you send this report at the end to the LLM with the code, with the scenario. And then here is the final results of that specific iterations. And as you can see, it can pass all of those difficult scenarios for this function. And in this case, it's GPT. But recently, the new, and this is an experiment from 2 years ago, and the LLMs, they are more and more powerful right now. And then at the end, it also gives you the test report. That was regarding the rule-based software. And the conventional software architecture, the modular architecture, in that most of the software is rule-based. There are also machine learning-based. But more and more, the machine learning-based software is eating the whole architecture, and it become, at the end, the final goal is to have something similar to this, the end-to-end. And then you might ask that, then what do you do? The first point is that I think rule-based will still exist in even these kind of architectures to safeguard these kind of models. But for that also, you remember that in the hazard analysis risk assessment, I mentioned that we come up with the critical scenarios. And in order to translate those critical scenarios into the some kind of machine, into the training of machine learning, you need data. And data in machine learning is basically the requirement, the implementation. Data is everything. So if I show one of the weaknesses, or not weakness, but one of the characteristic of these kind of models is that, for instance, here, we did an experiment on YOLO, the latest version. And if you show to the YOLO some of these scooters, they don't detect them. They detect them as a pedestrian or a skateboard, but they don't have any class regarding the scooters. And this is something that is because of the distributional shift. And it means basically that the environment is changing, but maybe your implementation is not changing as fast as those aspects. And this is basically YOLO. So you train your model based on all of these white swans, but there are a lot of black swans or unicorns that you can come up with them in your hazard analysis risk assessment step. So how do you create them? So there are multiple ways. There are AI-based, basically generative-based models, but one of the models that is mostly rule-based is the 3D Gaussian Splatting. In that way, from the recorded data, you can create a 3D representation of your data, and then you can use those 3D representations in order to change those scenario or reconstruct them in a different way that you want to do. For instance, you can remove some of the objects, or you can change the trajectory of them. Here is one example. Basically, the top one is the real world data, and the lower one is the reconstructed, rendered one. And you can see that the difference is not that understandable, especially if you are going in your original viewpoint. And then you can change the trajectory of any of those agents to create critical scenarios, like this case. And as you can see, sometimes when you have the objects from the different angles, you have a bit of the strange shape of those when you render them, because basically the model didn't see all the aspects of that. And then you can use other techniques, like, for instance, right now we are looking at diffusion-based models to basically improve those as well. Or you can change the pedestrian, for instance, in this case, trajectory, and create safety-related scenarios. So in simple words, basically you can reconstruct the whole model, remove or add new objects, or you can modify them. Something that we did also was that we extracted these items from the real world and we injected them into the simulation environments. And in that way, you can also, instead of developing the assets by yourself in the game engine-based simulation environments, you can use those in your simulation. Yeah? Thank you.
Ali, thank you so much for that very, very interesting presentation. Thank you very much.
And I stayed in 20 minutes, so
yeah,
and I
excellent.
had 60 slides, so that's good.
That's great. That's great. Excellent work, really. That means we do have time for just a couple of questions, if that's fine for you.
Sure.
So first of all, I want to start off by asking you, so how much of a game changer are these VLMs when it comes to data collection for autonomous vehicle development today? Like, how much does these models actually speed up development today?
Yeah, actually, one of the interesting things with respect to LLMs and VLMs is that for sure, for anything that we already know that exists, we can always come up with the rule-based aspects. But the issue is that one of the difficulty of our area is that you don't know always what is going on outside. The advantage of LLMs and VLMs is that they are trained on vast amount of data from the internet, and then they know most of these unknown scenarios, maybe for your specific domain, but in your domain is unknown, but for them it's not unknown. And then for sure they have hallucinations, they can guess, but also they are more, that ability is really important for us, especially when you want to do monitoring of the field operation. So for instance, one of the experiments that we did was that we used VLMs to see that if this specific environment is inside the operational design domain or outside, because sometimes it might be difficult also to understand that if you are inside the operational design domain or outside. And I don't say that they basically precision recall and this kind of stuff is 99%, but still it can raise a flag for you that there is something strange there. And I know that for basically the data annotation and those kind of aspects, they are also used. Yeah.
Right. Thank you so much for that answer. And the next question is, so this is an interesting one, I think. What's an acceptable ratio of synthetic data to real-world data? I feel too much synthetic data might lead to a lower model performance.
Yeah, that is a question that you can ask from Zensact. I don't know the accurate answer, but I think that if you have the luxury to have real-world data, enough diverse and enough coverage of all the scenarios, then that would be fantastic. But the issue is that you don't have that luxury to have all of those combinations of these agents that they interact together. So that's one of the reasons that we want these synthetic data generations. Yeah, but how much is allowed to use that I don't know.
Right. Thank you so much.
Sure.
And with that said, we want to thank you so much for holding this presentation, and we want to give you this umbrella as a
thank you.
Thank you so much.
Thank you.
Thank you.